Hello, everyone. Uh, we just finished the prior chapter, so we're going to be starting this discussion in this chapter, which focuses on functions. Today, we're going to be looking at functions, notations, and then their graphs. If it hasn't happened already, please make sure that our guest teachers passed out the Chapter 2 note packet, because we're obviously going to be in Section 2.1 today. And then you should also have the assignment sheet for the chapter so that you would know what the assignment is corresponding to Section 2.1. So pause the video now if we need to do that. Otherwise, I'm going to continue forward, assuming that we've got the note packet to follow along. So here we go. We're going to do a little warm-up discussion. If I were here, I'd actually have you move to these corners, but since I'm not, I'm just going to have you kind of play the game in your mind. Imagine that I assigned each corner of the room a letter. Let's call the back corner by the Chromebook cart corner A. The opposite back corner would be corner B. Let's call the corner by my desk, corner C, and then the corner by the door, corner D. And I would have asked you to go to your corresponding corners based on this rule right here, or I guess these series of rules. So it would say if you walked to school today, go back to corner A. If you rode your bike to school today, go to corner B. If you drove or rode in some vehicle, go to corner C. If you got to school any other way, if you hopped or skipped or scootered, go to corner D. So then you'd think, well, actually go ahead and do it right now. Think where you would go to. I'd ask you to go and then ask you to come back to your seats. We'd play the game a few more times. So the second round would look like this. I'm going to cut it down to just two corners, corner B and corner D. And instead of asking you how you got to school, I'm going to ask how long it took you. So I would say if it took you less than 10 minutes to get to school today, you would go to corner B. If it took you 10 or more minutes to get to school today, I'd say go to corner D. So again, in your mind, think which corner you would go to. You would go, you'd look around, and I'd say, okay, go back to your seats. We're going to play one more last round. Here's the rule for the last round. This one's going to be based on color of clothes that you're wearing. I would say if you're wearing blue, just go to corner A. If you're wearing red, go to corner B. If you're wearing black, go to corner C. If you're wearing white, go to corner D. Maybe go ahead and think right now, which corner would you go to? As you think for this one, you might realize that there's a problem with these series of rules that didn't exist before. Do you notice? The problem is some of you might satisfy more than one of these conditions. What if you're wearing, for example, blue and red, and then you're deciding if you're going to go to corner A or corner B? That would be a bad rule because you don't know which corner you're going to go to. So we have one of you, which are acting as the inputs, that are trying to go to more than one corner. You're trying to go to two corners, and the corners are the outputs. So we would say that's a bad rule because you don't know where to go. We have a name for this in mathematics. It's called a function. So good rules in math are where each input knows exactly where they're going to go, has only one output. So that's what a function is. A function is a pairing of inputs with outputs such that each input has exactly one output. You can think about this as the following. You can think about birthdays. Each person only has one birthday. If I asked one of you what your birthday was and you told me it's October 10th, but then you also told me it was March 3rd, that wouldn't make sense, right? You'd have two different outputs for one input. That would be a bad rule. It's illogical. However, what can happen, and we'll look at this, is two different inputs, in this case people, can have the same birthday. That is possible. Two different inputs can then have the same output. That happened when I would ask you to go to the corners. Two different people might have been in the same corner. Maybe they both drove to school that day. That can happen, but what cannot happen is one of you cannot try to go to two different corners. One of you cannot have two different inputs. The collection of the inputs, in our case, when I was asking you to move around in the corners, was the people, and we call that the domain. It's the set containing all of the input values for a function. Usually that's the x-coordinates for an equation. So the domain is the collection of all inputs. For our example in the class, the domain would have been all of you, all of your names. The range is the set containing all the output values for a function. That's usually a y-coordinate because I give the equation x and it outputs for me a y. In our example of moving around the room, the range would have been the four corners. You could have gone to corner A, corner B, corner C, or corner D. That would have been the range. In the birthday example, the range would be the 365 possible birthdays in a year. So domain are the list of all possible inputs. The range are all of the possible outputs. If I look at a picture and I ask you what the range and the domain are, well, let's do the domain first. The domain is all of the x values that occurred. If you look at your graph right here, the farthest left x value is -4, and the farthest right value is +2. So the domain would be all values between -4 and 2. You could write it like this, -4 and 2. That would be the domain. If I asked what the range was, well, the smallest y value is 1, and the largest is 4. So I see that y goes between 1 and 4. I usually tend to write it outside of the actual picture. So I would say the range is any y value between 1 and 4. We'll practice more of those moving forward. So a couple examples, just determining whether each relation is a function. So the domain, these are my inputs. For example, when I provide 1, I get an output of 4. When I provide 3, I get 2. When I provide 5, I get 4. When I provide 1, I get -4. But you'll notice when we gave 1, sometimes the output was 4, but sometimes the output is -4. So no, this is not a function. If it's no, you need to explain why. The reason why is because 1 has 2 different outputs, and that's a bad rule. We care about that in mathematics because we use functions to make computer programs. If I give a computer the value 1, it needs to know that it's always assigning a value 4 to it for a specific equation. I can't just give it 1 and have it sometimes be 4 and sometimes be -4, and the computer doesn't know exactly when it should be one or the other. Second example, -2 goes to -3, 0 goes to 6, 3 goes to 6, and 4 goes to 9. The rule that I'm looking at is that each input only goes to one place, and that's exactly what happens here. This is a function. Some of you might be wondering, well, what about the fact that 0 went to 6 and 3 went to 6? That's okay. That's like two different people having the same birthday. That's like two of you going to the same corner. It's not that 0 is going to 6 and then 0 is sometimes going to -3. That doesn't happen. If that were, for example, if there were an extra arrow going to like that, then this would be not a function because 0 is told to go to -3 and 6, but that wasn't the case in the original. Last one, maybe I give cities and the corresponding y value would be the state. So Helena goes to Montana, Boise goes to Idaho, Butte goes to Montana, Pocatello goes to Idaho. This is a function. Each city only has one state corresponding to it. It's okay that Helena and Butte both go to Montana because those are two different inputs going to the same output. It's not like Helena is going to Montana and then sometimes Helena is going to Idaho. So we have a no, a yes, and a yes. What about graphically? Let's use some numbers. So let's call this an x value of 1, then 2, then 3, then 4, then 5, then 6. Here's the y values of 1, 2, 3, 4, 5, 6, 7. Here's an x value of 2. Where is 2 told to go to? 2 is told to go to 5. That's fine. 3 is not going anywhere. 4 is told to go to 4 and 6. So there's a problem right here. And actually there's a problem with 6. 6 is told to go to 3 and 6 is told to go to 7. This is not a function. 4 and 6 have multiple outputs. That's a poor rule. In mathematics, we would say not a function. We actually have a specific test for this. It's called the vertical line test. I'm sure you've heard of before. It says that if you scan a graph, if there's ever a location where a vertical line would hit that graph in more than one point, it means that there's some x value that has multiple y's, and therefore that graph is not a function. So it fails right here, fails right there. That's all the vertical line test does. It's like a shortcut for remembering what the rule is that you're checking. The vertical line test, like I said, is used to determine if a graph is a function. But you can always just remember all your testing is to see if any x value input has more than one y value output. If a vertical line intersects the graph more than once, it is not a function. That's what the vertical line test is testing. It's used to determine if a graph is a function. If a vertical line crosses the graph more than once, it is not a function. Let's zoom in on this specific case. So here's my vertical line that I'm using to test. It's like a barcode scanner. If I go scanning, is there any x value that has more than one y? No, there is not. This one is a function. We call it a quadratic function actually. What about this over here? Well, it starts off okay. Look, 0 goes to 0, but then every other place I go this way has an x value going to a positive y value and a negative y value. So this fails all over the place over here on the right. So this is not a function. Last one. Let's do the easy parts first. Over here on the left, you'll notice every single x has only one y. They all go to the same y value, but that's okay. But each x only goes to one y. Then I'm going to hop over the middle, not worry about that right now. Over here at the positive x, again, they all only have one y. It's okay. They all go to the same y, but that's fine. Now let's look at the middle, okay? So right here, there's an interesting case. 0 for x is either going to go to the positive or the negative value, but you'll notice the positive value has an open circle. Why do we use open circles? Because open circle means do not include. Filled in circles means include, so that actually tells us where 0 is going to go. If I use numbers, let's say that this is like -1 and this is +1. If I asked the x coordinate 0 where it should go to, it knows because this is filled in down here that it should go to -1. So actually, this x coordinate of 0 only has one place to go to. It's going to -1. So this is actually a function. What one change could you make to this graph to make it not be a function? If you wanted it to not be a function, you would just fill this in. And then when you went scanning, right here, 0 would be equally valid in going to -1 or +1. So then therefore, that graph would not be a function. But the way that was originally written, it was a function because the x coordinate of 0 knew it should go to the negative value. That's how you can test graphs. Can give you a chance to try. So determine whether each relation is a function and state how you know. If it's a no, you need to say that this input value has more than one output value. If it's a yes, you need to write why based on the definition of a function. So let's pause the video now for maybe, let's say a minute. Unpause it after a minute once everyone's had a chance to try on the whiteboard. So pull out your whiteboard. You don't, yeah, so just pull out the whiteboard, give it a shot, unpause the video after a minute to see how you did. Okay, I'm going to assume everyone had a chance to try. This first one fails. -5 has more than one output. -5 is told to go to 3, and it's told to go to +5, so you'd say no, your justification. -5 has multiple outputs. Therefore, it's a bad rule. It is not a function. Over here, because it's a graph, you could use the vertical line test, go scanning, and every single x value only has one y value, so this is a function. You could say passes vertical line test. Or you could say each input only has one output. Some of you may have taken like pre-calc before, or maybe at the end of your Algebra 2 course they talked about it. This is actually the sine function. That's how we determine whether relations are graphs. Now moving forward, we're going to talk about a notation that we use for functions. It's a shorthand way of writing a lot of information. So consider the following situation. Let's say I had the equation for a line, because we were studying linear equations in the prior chapter. Let's say I have y equals 5x plus 3. I want to find the value of y when x equals 2. That's a lot to write, but you understand what I'm saying. You understand that I just mean substitute 2 in for x and tell me what you get. You end up getting 13. So you would say y is 13 when x is 2. That's still a lot to write. Watch me write it, right? I'll say y is 13 when x equals 2. I can do it, but it's a lot to write. Second one, almost exact same question. I would have to write it all out or say it, just adjusting the very last number. If y equals 5x plus 3, find the value of y when x equals 8. That means put 8 in for x. 5 times 8 is 40, plus 3 is 43. I would reply back by saying y is 43 when x equals 8. That is cumbersome to do over and over again. It's a lot of writing, it's a lot of verbiage. So the mathematics community has developed a shorthand notation for writing this. We're just going to name the rule. And we use the letter F typically. We also use letters G and H, but F because these are functions. So instead of writing all of that out, all of that meaning this part right here, and even this part at the end, we can simplify the process by naming our function f, or typically whatever you really want to call it, and then writing if f of x. That's how this is read. This is read as f of x. It does not mean f times x. F is just the rule. In parentheses is the variable that we're using for our equation. So in this case, you can see x is in the equation. Our variable is x. We write f of x is equal to 5x plus 3. When I put a 2 in the parentheses now, it means instead of putting x in for my variable, I'm going to substitute in 2. I get 5 times 2 plus 3. That is 13. That's the same thing I wrote up here. This whole statement right here has now been replaced by that. This f of 2 is a lot shorter to write than if y equals 5x plus 3, find the value of y when x equals 2. Now, instead of writing this little part at the end, y is 13 when x is 2, I can just write f of 2 is equal to 13. This means when x is 2, y is 13. F is just the name of the rule. The x coordinate is the input, the y coordinate is the output. One more example, instead of writing this second example all the way out, I would put in 8 for x, because 8 is in parentheses. I get 5 times 8 plus 3 is the same 43 I got before. A lot less to write. Instead of writing this whole mumbo jumbo right here, I could replace this whole statement right here by the statement f of 8 equals 43. When my x coordinate is 8, my y coordinate is 43. That's why we use function notation. It's a shorthand notation. It's more efficient. Just interpreting graphs using domain and range. So if I give you a picture, you should be able to state what the domain, the range, and f of 0 is equal to. That means what is the y value when x is 0? It's saying for the graph f or function f, when x is 0, they want to know what is the y value. So we'll do domain and range first. So here's my picture. Domain is how far my graph goes on the x-axis. So the farthest left it goes is to -2. The furthest right it goes to is 1, but it's open there. So I get any value for x between -2 and 1, but it's open at 1. So I would write it as this: -2, including -2, all the way up to 1. You could also use the bracket notation of -2, comma 1, but it's a parenthesis at 1. Either one of these you could use to write as your answer. You can use the, they call it interval notation, or you can use bracket notation. Your range, the farthest you go down is 1, and that's an including, all the way up to 5, and that's an including because it's filled in. So I would say any value between 1 and 5 for my y value. If I want to use brackets, it would be bracket 1, comma 5 bracket, because they're filled in circles. So that would be my range. My range is my graph goes between the y values of 1 and 5. Last question is, what is the value of y when x is 0 for graph f? That's the name of the graph. This graph is named f. So when x is 0, my y value I can see, well, that's just my y-intercept. F of 0 is just always your y-intercept. It's 1, which is saying when x is 0, y coordinate is 1. That is just your y-intercept. So when they ask for f of 0, they're just asking for the y-intercept because they want to know what's the y-coordinate when x is 0, which is the y-intercept. Okay. One more. My domain, my x's go from my furthest right is 4, and then as I go to the left, it keeps going further and further to the left, negative. It's going to negative infinity. So I could say, negative infinity all the way up to 4 including it. Or if I want to use bracket notation, I use a parenthesis because I really can't reach negative infinity, comma 4 I reach, so it's a bracket. So either one of these would be a fine way to write that. The range, or my y value, is my smallest y value is 0, and then technically this graph is going up and up and up and up, just slowly, but it's going up the whole way. So my range is the smallest y value is 0. It gets 0, so I put an equals to part. And then it keeps going up and up and up, so I'd say all the way up to positive infinity. If you want to use brackets, you would say bracket 0, all the way up to up and up and up, trying to get to positive infinity. So either one of these would be a fine way to write your answer. And then f of 0 is your y-intercept when x is 0. Your y-coordinate is 2, so you would say 2. Your y-intercept is the coordinate 0, 2. Last part is just interpreting a graph using function notation that has some context. It says below is a graph of how the HIV virus affects T cells. T cells are used to stimulate the immune system to produce antibodies. So over here, if you look, the graph is time after infection has occurred. And then on the y-axis, it's your T cell count. So you'll see once you've contracted the HIV virus, your T cell count tends to trend downward. So the first question is asking us to find and interpret f of 8. So they're asking when the x value is 8, what is your y value? Well, that's the point right here. I see when x is 8, my y value is 200. So it's f of 8 equals 200, but now they're asking me to interpret. So it would be this. 8 is years. So after 8 years, the T cell count is now at 200. This is per milliliters of blood. Last one, it's kind of the reverse. They say for what value of x is f of x the 350. So now they're giving you the y coordinate and asking you to find the x coordinate. So 350 would be this is 300 right here, so 350 is going to be somewhere in between. So when is it 350? Probably right about here. It looks like 6 would be a good estimate. So we would say f of 6 equals 350. So we would say after 6 years, the T cell count is 350. That's what it means to write it in context. It means explain it in the scenario of what we're talking about. We're talking about years, and we're talking about T cell counts. Last one, I'm going to give you a chance to try to make sure you're all good and set up to be successful for the homework. One, I'm just asking you to evaluate with function notation. And then one, I'm giving you a picture asking you to state the domain, range, and state what f of 0 are. So pause the video now, give maybe everyone, say, 2 minutes to try it. Unpause it after everyone has had a chance to try, and we'll see how we did. Okay, here's the first part. F of 10 is equal to, you just substitute 10 in for x, you get 30 minus 7 is 23. So this is saying f of 10 is equal to 23. When your x coordinate is 10, your y coordinate is 23. You know the point 10, 23 would be on this function, but you actually know this function's a line. So it'd be on that line because it's written in y equals mx plus b form. Over here, your domain, the smallest x value you get is -2. The largest x value you get is 6. So your domain goes between -2 all the way to 6. Your range, the smallest y value, is also -2. That's just coincidental, doesn't always happen. All the way up to 6. Hey, they have the same domain and range value. And then the last part asks us what f of 0 was. When x is 0, y is 4. So I would say f of 0, f of 0, you know the point 0, comma 4 is on the graph. It's actually the y-intercept. So there you go. That's what you should have got. You are now on section 1 for chapter 2, so 2.1. I will get the homework up here, hopefully. The program will work with me. I'm going to, maybe not. Come on. Well, if maybe not, you might just have to end the video now. You should have enough to be able to do the homework. You'll be able to ask questions when we come back on Monday anyway. So I'm going to try to get the program responding. There we go. Okay, so homework answers are right here. If you want to pause the video so you can be checking your answers, that sounds fine by me. Otherwise, I will see you when I get back. Thank you very much and have a good day.